Hi, today I would like to take a closer look at the RD JDS-6600. It was delivered to me this week from AliExpress, the regular channel I would almost say. This is the 60 megahertz version of this DDS signal generator / counter. And it was delivered actually within the expected number of days. The expectation was 12 to 15 days, and actually it was just delivered in just under a week, so 6 to 7 days I'd say. It's a very small box, very nicely packed. To give you an idea of the size, the height of the case is approximately 7 centimeters. The width of the whole thing is approximately just over 20 centimeters, and the depth is also just about 20 centimeters as well. Let's just switch it on, and this is what you get. Nice color display, and I didn't take the version number or serial number. Let's see, there's a system button here. What does it say? It's the model JDS-6600-60M. It's probably an indicator for the 60 megahertz, and part number 17269600099 for those who are really interested. So far I have been unable to find any version number for the software. So let's just take a closer look at this baby. So here's the power plug that comes with the signal generator. If you take a closer look, it is a model, what does it say? Very small print. Bravo Sierra 12W, long number, input 100 to 240 volts, 50 to 60 hertz, 0.3 amps max. That's on the input side. On the output side, it reads output 5 volts, max 2000 amps, 2000 milliamps, with the positive on the inner side of the barrel, and it has the CE logo, as we all can see. Very, very, very nice. So let's just see what this thing produces. You may notice that it has the American type of plug here, and it does come with a converter that you can use to use this kind of plug in Europe. So by now I have put the adapter in a power outlet. It is currently getting its 220 volts, and it's connected to the multimeter, which tells me that it is outputting 5.12 volts. Very nicely, it's living up its promises. Taking a bit of a closer look, I also have connected it to a constant current load. Currently it's not connected, it's measuring 0 amps. So let's just load this thing and see how it behaves under load. So here we go. Yep, there we go. The current load is currently taking just above 1 amp, and at that point the output voltage is dropping to exactly 5 volt. Not too bad at all. So let's just take a little bit of a closer look here, as we may also want to see what kind of ripple is on the signal. So I have also connected the power supply to the oscilloscope, and in this setting, let's just see, it is vertically at 0.5 volt per division, and I see no ripple at all. If I just disconnected, there we go, we see a nice 50 hertz when the input is floating around in the breeze. So connecting it back, I see no ripple. So let's increase the sensitivity, and yeah, we do see a little bit of a 50 hertz ripple there. I would say, that's about 2 divisions at a sensitivity of 10 millivolts per division. So There's about a 20 millivolt, 10 to 20 millivolt ripple when this baby is loaded at about 1 amp, and there is some high frequency noise on that visible, which is probably about the same amplitude, I would say. I have not been able to trigger on it, so it seems to be very noisy. So what can I say? Not too bad. Yeah, well, these are switch mode power supplies, so there will always be a bit of HF noise on that, as well as a bit of ripple if you load it. I see no trouble at this point though. Playing with this a little more, I was able to kind of get a stable picture. Thank you very much to all these analog scopes that we still have laying around. We are currently looking at 10 millivolts per division in a vertical sense, loaded still with 1 amp, and we are at 10 microseconds on the time base per division, which means we have a full period here of 1, 2, 3, let's say 3.5 times 10 microseconds. That's about a period of 35 microseconds, which is in the 30,000 hertz or 30 kilohertz range. So looks like this power supply is switching in that range, in that frequency range. Not too shabby at all. I would even consider that to be a bit low. I would have expected a slightly higher frequency maybe, but anyway, no trouble found. So ready to take a look at some sine waves out of this signal generator. If you switch the thing on, by default both channels are enabled and outputting signal. The default frequency that you typically get seems to be 10 kilohertz and an amplitude of 5 volt. I currently have connected the outputs to a oscilloscope, and just taking a little bit of a digital look at that here at the Rigel. And if we just take a little bit of a closer look at that, we get to see that there is this 10 kilohertz. The blue line at the top is the channel 1 from the signal generator, and the purple line at the bottom is the channel 2 output. The oscilloscope is at 5 volts per division for both channels, and the counter in the scope is currently measuring exactly 10.0000 kilohertz for whatever that's worth. Let's just see if I can get a slightly closer picture of that without making too much of a mess of what you get. So going up a little bit, there we go, there you are, and I can get you a little bit closer there. So if I just increase the frequency, we can go to like 20 kilohertz for channel 1, that's the top line, and 30, 40, 50, 60, and you can see it's triggering on the channel 1. So let's just turn off channel 2. So there we are. And just we see still a output of 1, 2, almost 3 vertical blocks, so that means we're still very close to 5 volts peak to peak. Increasing the frequency, 130 kilohertz, and the counter on the scope is saying 130 kilohertz. Looks good. Let's go to 200, see what it says. 200.001 kilohertz. Just changing the time base a little bit. There we are. And let's just further increase the frequency. 300 kilohertz, 400, 500, 600, 700. So let's just go to 1 megahertz. and it is measuring 1.000 all zeros megahertz. Pretty nice. Let's just increase the frequency. We can go all the way up to 60 in the end, right? 2 megahertz, 3, 4, 5, 6, 7, 8, 9. Wow, we're at 10 megahertz right now. And increasing. 20 megahertz, 40. Hey, and the counter is currently not indicating 40 megahertz, but this might be an issue because it's officially a 50 megahertz scope. So we might be running against the limits of the oscilloscope. Here we still see a very nice sine wave. But the amplitude actually is dropping. Now we are at 60 megahertz. Let me just get a little bit closer to the scope and give that a slightly better view. Increasing the amplitude. We are seeing 500 millivolts per division. And we have 1, 2, 3, 4, 5, 6, let's say 7 times that 3.5 volt peak. While it officially says that it's 5 volt peak to peak according to the signal generator. So yeah, this might be where the edges come into play and we might be hitting the limits of our box. Let's just take a further look. So at this point I have connected the signal generator to the oscilloscope and I'm ready to connect it to a 50 ohm dummy load as well. It's set at 10 megahertz and I do see a 5 volt peak to peak at 10 megahertz. If I just connect the dummy load to it, always a bit finicky, it drops to 2.7 volt peak to peak on the oscilloscope, which is approximately what you would expect because at 50 hertz, at 50 ohm, you would expect it to see about half of the output coming out of there. If we just increase the frequency and we go to 20, 40 or 50 megahertz, we see 3.6, 3.7 volt peak to peak, whereas unloaded it should be approximately 5, which is 4.5 volt approximately. So yeah, the output of the signal generator seems to be about 50 ohm for most of the common output frequencies. Let's go just to very low frequencies for a change and see if that appears to be true there as well. Going back to 10 and then to 1 megahertz, maybe even lower than that. 10 kilohertz, 10,000 hertz. Is what we are at. Let's say all connected. There we have it. 10 kilohertz, and we see 5.2 volt peak to peak. Loading it with 50 ohms, we see it dropping to 2.6 volts peak to peak, which is a value that is as expected. So right now I have changed the setup again and connected the signal generator to a directional coupler, which goes into the 50 ohm, and from there it goes, it looks at the forward signal from the directional coupler, which goes to my spectrum generator. And what you see here is actually 3 peaks. The top peak to the left reads minus 29.9, so say 30, minus 30 dBm. Keep in mind this is through my directional coupler, which has a substantial loss there. And the first harmonic at 20 megahertz, which is the second peak here, is marked and reads minus 74 dBm. That means 30 to 74, that is like 43 dBm down. And the third harmonic at 30 megahertz is at minus 76 dBm. So not too shabby at all. So by now I have increased the sine wave frequency to 60 megahertz, and you can see the peak on the left is at 60 megahertz. I was expecting the next peak at 120 megahertz and so on, but funnily enough I do have a peak at 83.9, so say 84 megahertz. I don't completely understand that. It is a rather strong peak, which needs a little bit of further thinking where this exactly comes from. So at this point what I've done is I've connected the signal generator to the oscilloscope, and at the same time the oscilloscope on the purple channel has the output from the signal generator, and the blue signal at the top comes from an external 10 megahertz reference, which is locked to a GPS signal and is my kind of lab standard here in the home lab. And funnily enough, at this point you can see that the frequencies are not the same, although there is a small difference. I'm increasing the frequencies in 0.1 hertz per click, and you can see they're getting closer. And at this point I pretty much have reached the point where the frequencies are the same, and the signal generator reads just 9.999982. Let me just show that to you. Can you read that? Megahertz. So we're like 18 hertz off the 10 megahertz. If we just take a look at the scope, you can see that the frequency is drifting already, and as I've been playing with this over the last 5 to 10 minutes, what I notice is that as the unit seems to be heating up, the frequency drifts closer to the 10 megahertz, and it might be that the point where the whole thing reaches a temperature stable situation and the frequency remains more or less the same might be very close to the 10 megahertz. It's definitely not more than 20 hertz off, which isn't bad for a unit at this price. So approximately after 30 minutes, it seems like the whole thing is stabilizing, and you can see that the external reference signal as well as the signal from the signal generator are pretty much the same. And if I just take a look at the signal generator at this point, the frequency that we read is approximately 11 hertz off. So the accuracy after warming up for about 30 minutes gets in the 1 ppm range. I'm getting enthusiastic by the minute about this little and interesting bit of measuring gear. So I'm currently back to having 2 channels connected to the oscilloscope, where the oscilloscope currently is in XY mode. So one channel is driving the X direction, whereas the other is driving the Y direction. And you can create nice pictures known as Lissajous figures. So to be able to play with that, what I have done is both of the frequencies of both channels are set to 10 megahertz, amplitude set to 3 volts at the moment, and the phase has been set to 0 degrees. So A and B, channel 1 and channel 2 should both be kind of completely running the same. Well, if you do that in the XY mode of an oscilloscope, let me get you a little bit closer here. The right altitude, there we go. And maybe even a little bit closer than that. You can see that the signal goes from left bottom to right top. And if I just increase the phase shift between the two signals to 1, 2, 3, 4, 5, all the way to 90 degrees, you can see that slowly a circle starts to appear. And that means that the signal is currently just 90 degrees shifted compared to the other signal, which in XY mode creates a perfect circle. This is a very well-known thing. If you'd like to know more, do some Googling for the term Lissajous figures. If we actually now would just change the frequency, you can create all kinds of funny pictures. Let's just go there. It's like almost a piece of art, right? Channel 2 is 10 megahertz, whereas channel 1 is 12 megahertz at the moment. And you can see that there's all kinds of nice pictures that start to exist here. Going back to both channels on 10 megahertz, we get a nice circle as expected. We could also increase both frequencies, both channels to like the same higher frequencies, say like 20 megahertz. Channel 1 going to 20 megahertz, channel 2 going to 20 megahertz, and we get a more or less nice circle yet again. Doing the same at 40 megahertz, channel 2 at 40 megahertz, channel 1 at 40 megahertz, and yeah, we pretty much have a nice circle. Going to 60 megahertz, maximum frequency for this little piece of equipment. Channel 2 to 60 megahertz, and you can see it's no longer a perfect circle. So yeah, subtle distortions and phase shifts may cause this. You can also see that the line is not as sharp as it was on the lower frequencies. Let's actually just go back and decrease the phase shift back to 0 degrees, so both signals are completely in phase. 20, 10, and here we have 0 phase shift. And what you actually can see is that, yeah, this is not a straight line. Actually, if I just go down a little bit further and make it a straight line, I have to go back to 352 degrees, in other words minus 8 degrees, to get the signals on a straight line and being completely in phase, which is kind of a measuring thing. Initially you could be thinking maybe it has to do with the coax cables, but the coax are both identical and the same length. I bought them a few years ago at a shop, both at the same time from the same batch, so there is no issue there. So more likely there is something in this signal generator which causes a slight phase shift at 60 megahertz. But hey, I'm not complaining at all. And again, I've gone to another mode. The sine wave has been changed into a square wave. I've gone up to the maximum frequency in the specification sheet, which is 6 megahertz for a 10 volt peak to peak signal. And coming out of channel 1, going to the oscilloscope without any further loading, I get this picture, which kind of nicely shows. Can I get that a little bit closer to you? Let's just see. Yeah, it should be possible. There we go. And you should be able to also read that. Looks all very nice, although not a perfect square wave, definitely. If we just zoom in a little bit on the horizontal, then you can see that there is a very clear rise time. We're currently looking at 10 nanosecond per division horizontally and 2 volts per division vertically. So let's just sort of see some cursors and do some measurements here. First of all, the verticals, maybe. Yeah, move that one a little bit to the left. That's pretty much where I have reached the plateau. Whereas on the other side, it's always a bit tricky if you're not using these functions too frequently. And here you can see that we've kind of nicely boxed it up, and we have spent about what is it vertically, 23 nanoseconds to go from 0 to max 10 volt peak, which is a very good rise time, but it's definitely not a perfect square wave. So if this is important for you, keep an eye on that if you're using this square wave for further experiments. Interesting detail about this measurement is that this picture looks exactly the same, except for the fact that the frequency of the square wave has now been lowered to 100 kilohertz. So if you're just if you change the amplitude, yeah, you can see that changing as I just play with that on the signal generator. But if you just play with the frequency, you can see that there is almost no difference here. Oh, there's a 0. There we are. So the rise time seems to be part of the device and nothing to do with the DDS that creates the square wave. It might just be the amplifier on the output here that is causing this to not rise any faster, which can perfectly be understood for a device like this. An interesting thing that has been mentioned with this device and cheap signal generators in general is the use of the DC offset with the output signal. Currently the signal generator is set to 100 kilohertz, 15 volt peak to peak. It can be moved up to 20 volt peak to peak, and an offset which we are varying. It's currently set at 2 volt. Let's just keep an eye on the oscilloscope to see what happens if we increase the offset. Move to 3 volts, 4 volts. Hey, there is a flat top, and the flat top moves stronger if it goes to a 5 volt, 6 volt offset. What actually is happening here? By the way, for your information, the input for the oscilloscope is set to AC, so we're not getting any DC signals visible there. But if the output signal goes over a limit value, which for this device seems to be just shy of 20 volts, the signal doesn't go any further and the signal just flattens out at the top. It's currently set at 6 volts DC offset, 5, 4, 3, 2. But for 2 volt it seems 3 volts it now. For 3 volt we see kind of an okay sinus. If we just change it to 4 volts, then it flattens off at the top, which means with a 15 volt peak to peak, we don't have any space above that 20 volt limit. We should be able to see the same if we go just down to minus 4 volt, and yeah, we do see a very similar thing happening there. So be aware, this is not shown on the display of the device. You just don't get a perfect sinus coming out, which you might be expecting. So be wary that you're only having like a 20 volt peak to peak space. If you're just changing the output amplitude to 20 volts, let me just do that. It is 20 volts right now. And if you have that setting, pretty much any offset, it's at -1 now, it's at 0 now, we get a perfect sine now. But as soon as we change the offset, when the peak is set to 20 volts, you see this flattening effect happening on either side. So you may want to be aware, as what you measure might not be what you think you measure, and cause all kinds of confusion as you're using this device. It's a common thing, well known, shown in different other videos, but I thought I'd include it in this one as well, just to make you aware. So just a last view at this very pretty device. I'm pretty sure it will find a good place in the home lab here. I'm definitely going to use it for my HF experiments. The HD Sine signal are looking to be very useful here, and the 50 ohm output seems to be very useful as well. So the amplitudes are rather predictable. Together with some attenuators and the experiments that are ahead of me, this will be a very good friend for me in the time to come. This is a very warm welcome to my new digital signal generator. I didn't even look at the counter function, as I do have another counter and don't need that functionality so much. And this thing absolutely can replace my my old signal generator, which is out of the 1950s or 60s, an old advanced signal generator, which also does 60 megahertz, but is absolutely less reliable. So some space coming available there, and well, that one is goodbye for now, and a warm welcome so to the new device that we've just taken a look at in this video. So that's it for now. Hope to see you again in YouTube land. So bye bye.